Okay, so good afternoon to everyone. First of all, I would like to thank the organizer for setting up this beautiful workshop and for giving me the opportunity of presenting my results. So I'm Giovanni Ferioli. I'm currently working in Florence as a tenure track researcher, but all the results I will show you today has been achieved at the Institut of Dicke, where I was part of the light scattering experiment in the quantum optics team led by Antoine Brouwys and Igor Fierro-Barbut. And here you can see all the people that have contributed to the work I will present you today. So Antoine, Igor, Sara Pancaldi, and Antoine, the other two PhD students. And we have also very fruitful collaboration with David, who is here in the audience. So the general goal of our experiment is to investigate collective effect in light scattering. Let me start by defining what a collective effect is. The interaction between light and a single atom is something which is pretty well established. We all know that if we have a two-level system and if we drive it resonantly, it will undergo Rabi's oscillation, which is described by the optical block equation. And we all know that after the switching off of the driving, the probability of finding the atoms in the excited state will drop exponentially with a time constant that depends only on the line width of the atoms that we are illuminating. However, if we are considering many emitters, the situation can be dramatically different, and we can define a collective effect as everything which is not described by these. And the first historical example of this collective effect has been pointed out by Dicke, and it's superradiance. We have already heard a lot about this, so I will not present you the main idea beyond Dicke model, so I will skip some slides. But I just want to highlight a couple of things, which are the following. So Dicke model, it's pretty nice, but of course it's not the full story. And there are many reasons for that. The first one is associated to the fact that in Dicke model, he has considered a cloud of atoms promoted to the excited state and enclosed in a volume smaller than lambda. But actually, this regime is pretty challenging to be achieved in experiment, especially working in an optical domain due to the diffraction limit. Moreover, when an atom is illuminated by light, it will develop a dipole. And dipole belonging to different atoms interact via the so-called light-induced dipole-dipole interaction. And actually, also this effect has not been considered by Dicke, and the combination of these two leads to a coupling from the symmetric state of the Dicke letter to the other state of the Hilbert space that are the so-called subradiant state. Moreover, he has considered atoms promoted to the excited state, but we all know that they typically are in the ground state, so also it's not clear what is the effect of an external driving in this picture, coherent driving at least. And finally, everything that in the Dicke model, it's mainly associated to the spin, so to the atomic degree of freedom. But what about the light? So what happened to the light emitted by this system, this superradiant system? And actually, in the last year, we have the opportunity of studying some of these effects, and this talk will mainly be associated to this last point. So what is the light that such system emit? Let me just now introduce our experimental platform. I'm working with Antoine, so we are using optical tweezer, and specifically here, our setup is characterized by two couple of high numerical aperture aspherical lenses forming a so-called Maltese cross configuration. And we use two of them to create a single big optical tweezer where we are able to trap up to 5,000, 6,000 rubidium atom at a typical temperature of 200 microkelvin. And then what we typically do is to shine a strong magnetic field. We perform some hyperfine and Zeeman optical pumping, and then we shine line resonant to the closed transition in this stretch state so that the system behaves as a cloud of two-level emitter. And then the typical measurement that we perform is the so-called time-resolved fluorescence. It means that basically we release the system from the trap to get rid of the inhomogeneous broadening, and we shine some resonant light, and we collect the light emitted in different direction due to this Maltese cross configuration with a nanosecond resolution and at the single photon level, so using avalanche photodiodes. What we see, typically we have something like that. So if we prepare our system, one thing that I forgot to mention, that the geometry that our cloud possesses is a cigar-shaped elongated trap, which has two sides, the radial one that are smaller than lambda, but the elongated one that is of the order of some tens of lambda, which means that we are below Dicke in two directions, but not in the third one, but still the volume is of the order of some lambda cube, so we are at the edge of the Dicke limit. So what we observe typically, so we create our cloud, we put some small atom number inside, and then we shine some resonant light. For all the measurement that I will present you today, the driving direction will be in a radial one, and the collection one will be along the main axis of the system. And by collecting the time resolved fluorescence, the typical temporal trace that we have is something like that, which is pretty well described by the solution of the optical Bloch equation, which is the black dashed line here. But then if we crank up the number of atoms, let's say by 1 order of magnitude, and we put 3,000 atoms inside, what we have is something different. For instance, you can see some collective effect appearing either in the coherent evolution at the beginning of the system, but also in the de-excitation process that happen after the end of the driving. And actually, in order to understand what's going on, we need to remind that what we are currently measuring is the photon emission rate, which is given by this formula here, that depends on two contributions. The first one are the photon emitted from the decay from the excited state to the ground, and the second one is instead the photons that are virtually exchanged between two atoms, and this accounts for the correlation hosted inside the system. And actually, in order to explain this kind of behavior, we need to invoke the presence of these, because the photon emission rate provided by this term here cannot be bigger than 2 times the steady state one, at least in the resonant and strongly driven regime where we are operating. And actually, in this paper here, we have carried out some ab initio numerical simulation based on the cumulant expansion, working on this formula here, and we actually verify that these correlations are not only present, but they are beyond mean field. So everything that I told you so far can be summarized like that. So we have some collective effect. They are mediated by the establishment of this correlation. The question now is, can we say something more by looking at the statistics of the photon emitted? In other words, is this correlation somehow imprinted also in the photon statistics? And in order to answer to this question, we set up an Ambury-Brown twist experiment, and we measure the G2 of the light radiated by this cloud. At the beginning, I will mainly focus on the steady state of this driven dissipative system. So in general, measuring G2, calculating G2 is pretty challenging, especially if we are dealing with thousands of emitters. But actually, we know that a simple limit exists, and it's the limit of uncorrelated cloud, where we know that the Sigar relation hold. We have already heard about this Sigar relation some days ago. But basically, this relation says that the G2 of a cloud of n independent atoms is 1 plus the modulus square of G1. And actually, the first thing that we did is to verify such relation. And in order to create a cloud of uncorrelated atoms, we create our system, we let him expand in free space for a long time, and we shine a very long pulse of light, and we measure the G2 here. So the cloud becomes big, the atoms are far apart, there are no more correlation, and in fact, what we measure is pretty well described by the Sigar relation. So here it's not a fit, it's direct comparison between our data and this relation here. And we have checked the validity of this Siga relation in a broad range of driving strength. So let me shortly show you where this relation came from. So in general, the G2 is given by this expression here, as we have seen in Ardo talks on Tuesday, which is pretty hard to be handled. But actually, if we consider that the cloud we are dealing with is made by uncorrelated cloud and that the number of emitter is high, we can assume the central limit theorem to be valid, and so we would expect the field to be Gaussian, the statistics of the field to be Gaussian, which means that we can take this expression and split it using the cumulant expansion, and we can read of all the terms that are proportional to cumulants larger than 2. And if one does this, we get to this ugly expression here, but then it's easy to recognize that this term, it's washed out because it's rotating fast in the time beam of our detector. And then we can make a second assumption, which is that the mean field radiated by the system is 0, or that the light is incoherent. And if one, so using these two hypotheses, we can recover the Siga relation. Okay, so then we go back to the lab and we perform the experiment in the dense limit. And actually what we find out is that in this limit, Siga relation doesn't hold anymore. And in fact, we observe something where the G2 of 0 is not 2, but assume a smaller value, and that becomes smaller than 1 in the oscillation. Unfortunately, this does not violate any of the criteria of quantum light, but still it violates Sigart. So it means that one of the two hypotheses over which Sigart is based are no longer valid in our cloud. So either the field that the cloud is radiated is not Gaussian, either there is a mean coherence. And actually both conclusions are not trivial in our case, because also for this one, so we are driving in a direction which is different from the collection one. So if we have a coherence, this is not imposed by the laser, but is self-created, let's say.
I don't understand. We can have diffusion, coherent diffusion, which is not in the direction of the laser.
But it should not be coherent anyway, no?
Yes.
Okay. We can discuss maybe later. I'm not sure I get your point, but
You send light on an object, it will diffuse, I mean, it stays coherent.
but I mean, you mean the photons cut?
Moving, so due to temperature, I think you lose this.
Yes.
Maybe.
I think yes. I think, and moreover, I mean, the mean free path of a photon is larger than the size of our cloud. So it's very unlikely that one photon emitted by one atom is scattered by another one. Okay, so yes. So what I will so to try to understand which one is the right hypothesis, let's say, we try to. I will bring you some experimental evidences of the fact that this one it's actually 0. Of course, they are not direct evidences. Because and actually one nice thing would be to try to measure the field, but we didn't succeed so far. But so if we assume a finite value of the field, it has to be given by this relation here, where sigma I is the mean value of the atom of the dipole I. But then if we drive strong enough, this has to go to 0. And so we would expect that if we have a mean radiated field, it has to become 0 by increasing the strength of the driving. And actually we try to drive as strong as we can, and we always violate Siga relation. Moreover, if this relation holds, it means that the mean radiated field has to scale like n, which means that the intensity has to scale like n square in the steady state. And we don't see such trend. Actually, we can also estimate the residual from the fit, and this is not enough to justify the discrepancy that we have in the measurement of G2. And finally, we have a third evidence, which is maybe a more direct one. So we can measure also G1 by homodyne detection. And G1 in the long time, it's a direct measurement of the field. Of course, we cannot probe a really long time, but in the time window that we can access, basically, the Fourier transform of the Mollo triplet works quite well to describe our data. And so we expect that this goes to 0 for longer times. And so this points towards a not Gaussianity of the radiated field as an explanation of this observation. And this also means that, of course, the statistics of the spin, it's also not Gaussian, because one, it's a linear combination of the other. Then we can assume the field to be not Gaussian, and we can measure directly the connected correlation. We have heard about them during David's talk. And actually what we find out, basically at this level, the connected correlation, it's basically the difference between what we measure and what we would expect from a Gaussian statistics. And what we find out is that by changing the number of atoms inside our cloud, the connected correlation goes to 0 or becomes smaller, as expected from a collective behavior. And actually these connected correlation are pretty interesting by a many-body point of view, and has been measured only a few times in hemophysics experiment. Okay, so this was the first part of the result I want to present you. Everything I told you so far has been measured in the steady state, as I was mentioning at the beginning, but of course it's interesting to measure G2 also during a transient behavior. And in that sense, the most intriguing not steady state behavior, it's the superradiant burst. And so we decide to measure the photon statistics during heat. So here we can use the Dicke model as a toy model to have an intuition of what's going on. So in absence of any driving, the master equation is this one. We have already seen this formula this morning. And this can be easily solved using QTIP, for example. And for instance, in the case of 6 atoms, we can measure the photon emission rate, which show the burst that I was showing you at the beginning. But we can also measure the G2, the equal time intensity correlation function, which show this peculiar behavior. Basically, it starts from something which is between 1 and 2. It goes to 1, and then it increases again. And actually, I find this nice, because this is another explanation of the word coherence in the title of Dicke paper, because it's the self-creation of a coherent light during the burst, if you wish. Yes, exactly, yes. Yeah, sorry for the notation. Okay, so we we performed the experiment, and first of all, so in order to do this, we apply a short pulse of light, which in our case is not so short with respect to the lifetime of the excited state, but it is the best we can do given the laser power that we have. And first of all, we observe a superradiant burst, which is not trivial. And we also measure G2. And actually, we observe something which is pretty similar to the result of the Dicke model, which is these two dashed line here, at least in the early time dynamics. So this can be interpreted as a phase locking mechanism. I'm sorry, it's not the same interpretation as what we heard 2 days ago, but it's also, for an experimentalist, it's also hard to say that here we have a fully entangled state, so I feel a bit more confident with this. But of course, and not only we observe the same qualitative behavior, but it is almost quantitative in the early dynamics. Here the theoretical model has been calculated using 6 atoms while we have 3,000. So why? The reason for that is that our cloud is emitted in the 4 pi, and so we need to consider the coupling of our cloud to a given diffraction mode, which is the one that we are measuring actually. And if one measures the diffraction pattern of knowing our geometry, it's possible to demonstrate that this coupling is equal to 210 to the minus 3, meaning that over the 3,000 atoms, only 6 are effectively coupled to the mode that we are probing. And that's why we are using this number for comparing the data to the theory. However, as you can see, it's also evident that the Dicke model by itself, it's not enough to explain our observation, which is kind of clear from the beginning, because all the hypotheses over which Dicke model is based are not verified in our system. And this is also clear in the photon emission rate, not only in the G2, because of the appearance of this subradiant mode that is populated during the decay. And this actually call for a full microscopic model able to describe our system, and I'm quite happy that people is working on this. And I would also like to stress that our experiment, it's not the only one seeing this effect. We have a very similar result observed in the team of Arno in Berlin, and I think that we will learn about this result tomorrow in a nanofiber. Okay. Yes. The last experiment that I want to show you is the comparison between what we have during a superradiant burst with what we measure during another transient behavior, which is this time what follows the steady state. So here we are sending a long pulse of light. We prepare the state in a completely different way. We have an incoherent superposition of atoms in the ground and in the excited state. We switch off the driving and we measure G2. And this, let's say, this decreasing value of G2 is absent in this curve here, meaning that this somehow it's really a fingerprint of a superradiant burst. Okay, with this, I move to the conclusion of my talk. So at the beginning, I show you that by measuring the G2 in the steady state, we were able to violate Sigar relation, and this seems to suggest that the statistics of the photons radiated by the cloud is not Gaussian. And we have measured for the first time this kind of, together with Arno, of course, this kind of the G2 during a superradiant burst. What next? Of course, it will be interesting to study similar effect with an incoherent pumping, as we heard this morning. And on the other side, it would be interesting to see to perform full tomography of the light emitted by the system to really benchmark the node Gaussianity of the light. Before concluding, just to put one slide about what I'm currently doing in Florence. So I'm currently working with Giovanni Modugno, and we are building a new machine to create Bose-Einstein condensate of dysprosium atoms. So we closed the vacuum at the end of last year. We have beautiful lasers, beautiful color. We have the 2D MOT, the 3D MOT in the intercombination line, and so we are ready to trap the atoms in the dipole trap and to reach the BEC. And the goal of the experiment is to study, by one side, the supersolidity, if you wish, in a strongly correlated system, so in a lattice. But we are also considering of performing some light scattering experiments, since dysprosium is an amazing candidate for this task. And with this, I'd like to thank all the people I work with, and I thank all of you for the attention.